So there are a few more things about the Linux kernel that I would like us to remember or be able to imagine as we move forward in this series. So, okay, first things first, let me get myself up here. All right, so we were talking about, things that we need to remember or we should know about the Linux kernel. So first off, the Linux kernel, I'll just write it as kernel here. It kind of operates in a privileged mode. What does privileged mode mean? It means that the Linux kernel and obviously the kernel here has drivers as part of it, so the kernel can reach out to the hardware, right? And this is important because, well, the Linux kernel is kind of one of the features is that it helps us manage the hardware. But the question is, why can't a user application manage the hardware directly? Well, the answer to that is we would not like the application to kind of take full control of the hardware. Then it can do whatever it wants. That is number one. And we would want to restrict it. We would not want it to do whatever it wants with the hardware whenever it wants to do, we wouldn't want that. And the second thing is we would like multiple applications to share a hardware. For example, let's say we have the solid state drive. The state drive has, let's say, some partition on it, and partition has various files on it. And then there are different applications that are wanting to access, different files. So all of them are essentially now wanting to access the SSD as a hardware. So, we wouldn't want one application to own the SSD or have like a lock on it or mess around and use it in whichever fashion it wants. We would want somebody to provide like a very nice, serialized and managed access to it. So that's one of the reasons the kernel running in the privileged mode has access to the hardware. And as you can guess, the applications run in unprivileged mode, right? So that then means that the application needs to talk to the driver, right? And application somehow needs to convey its intentions that, hey, I want to read this camera, and can you, copy over the buffer, the video buffer, or the frame, so to speak, to me, right? Can you give me that frame that's available in the camera? So the user application here needs to talk to the driver to do any interaction with the hardware. Now, around this point, I want to kind of just present a case for how CPUs are, and that will add like more clarity. So CPU, for example, the ARM A V8, based on the V8 architecture, the ARM A class of CPUs, the 64-bit one, and we also have like a free course on this, and that you can check and learn more about these CPUs. So the ARM A CPUs has something called execution levels, and the execution, or sorry, not execution, exception levels. And the exception levels are like EL1, EL0, EL1, EL2, and EL3. Now the Linux kernel in this case runs in EL1, right? And as you can imagine, as part of the execution level one, the hardware, the CPU is designed in ways that it can access different features of the CPU. For example, the status, like it was the addition a positive number, did the subtraction lead to like a negative overflow, did it or did the addition lead to like a overflow, did the subtraction lead to a zero, so on and so forth. Those kind of details are kind of captured in something called status registers. And the EL1 then, or the software executing in EL1 has access to those kind of things. And the kernel then runs here. The user applications run in exception level 0, in which case, as you can imagine, the hardware, when it's running in exception level 0, it turns off certain features. And so code running here cannot access such CPU status registers. I gave you an example of a status register. Some of them, the EL0 code can access. CPU configuration registers, for example, the EL0 cannot access. So now you can imagine the kernel is running here, the user code is running here, and so any access to the hardware that needs to be done, the control needs to be passed from user space, so to speak, which is this, right, from the user space down to the kernel space. And now here's another interesting thing that we need to know, which is from the user space to the kernel space, the control is passed or the requests are made via something called system calls, right? So system calls is how we essentially, from the user space, ask the kernel space to do something for the user application, right? So let's say we are wanting to do like a thumbprint verification or thumbprint based authentication. The user space will essentially ask the kernel space to kind of go, do something about the authentication process and just pass, yes or no, one or zero as the answer. So the user space app never accesses the thumbprint sensor, the fingerprint sensor, but the kernel does something around it, right? All right. And how does it do it? Or what is the way to request from user space to kernel space? It's system calls. And what are system calls? So system calls are essentially a bunch of actions. These are bunch of actions that over the years people have realized, the developers have, or rather the maintainers of the Linux kernel, the Linux kernel development community have realized are common or generic. So for example, we would want to perform read on, let's say, the camera buffer, and we might want to perform a write operation on the display buffer. Load data into the display buffer, read data out of the camera buffer. So read and write, for example, are such generic operations that we would want to perform on different hardware. So the system calls are those. So somewhere then, what we can imagine now is that the Linux kernel, the drivers within that, right, are somewhere supposed to implement the system calls, right? Somewhere they are supposed to, like when let's say we were asking, hey, can you read the image buffer of the camera, then we are essentially saying, hey driver, who is handling the camera, can you go and read that buffer for us, right? And so somewhere the device drivers, and this is key by the way, this is like a very important point. So the device drivers somewhere implement, they somewhere implement system calls, right? And we'll take a look at these in details as we develop the code, but this background information is an absolute necessary one for you. User space is something that you should remember, kernel space is something that you should remember, privileged, non-privileged, and the communication between these two happen via system calls. And we'll take a look at the system calls in detail as we write our drivers. And we also mentioned that the kernel has drivers and the drivers implement the system calls, right? So with this as the background, now let's take a look at how does the Linux kernel uh, house or hold the drivers within it. So let's call this D1, D2, D3, D4, and D5. And this is our kernel. So the idea is after boot up, if the kernel, whatever drivers it has, if it is using those, then we call them as boot time drivers. This is not a specific like this is not a standard keyword. I'm just coining a term here. Boot time drivers, or you can also say like built-in built-in drivers. This is like more accurate, honestly. Right. The second one, built-in drivers. And let's say if you have a piece of hardware like a camera system you're working on, or some new fancy device that your team is working on. So the driver for that won't be available in the Linux kernel community or in the Linux kernel source. So usually what happens is the developers, they will develop that driver and push it to the kernel mainline, right? They'll push it to the mainline, and then they'll kind of download and create like a new kernel image, right? New recompile the kernel. But when they're developing it, one of the ways that they can check whether their driver is working correctly or not is by injecting it or loading it into the live system, right? So you have Linux kernel running, you're writing a driver, you want to test it out, you connect the hardware. Well, right now the Linux kernel doesn't have any driver. You're writing that driver. Because of that, it doesn't have. Now, what you want to do is compile your driver and be like, okay, can I load it into the live system so that I can check whether my driver can handle that interactions with the hardware correctly? So those are called the loadable kernel modules. Modules, or you can also call them loadable kernel driver, right? And this is something that we are going to focus on as part of this course. But now when you're essentially developing this Linux kernel loadable module, the idea is that the Linux kernel provides you with a way, or provides all of us with a way to be able to load that in. And what does loading mean? And what does it mean that a driver is loaded and activated? You can imagine that the kernel allows us a way to specify how to absorb the driver into a live system, and then it kind of activates and initializes, and that is for later. As we dive into the code, we'll talk about how it loads and things of those nature. But one other thing I want you to imagine is the idea of constructor and destructor. I might have got the spelling wrong here, but the idea of constructor is when you initialize a class, so to speak, you execute, some initialization code, and as that object goes out of scope, we call like the destructor, and deinitialize or clean up the kind of memory that the object acquired, and so on and so forth. So this is coming from the object oriented programming world, but somewhere the Linux kernel provides some feature that is equivalent to constructor and destructor, and that's how, like, as we submit our loadable module, the initialization sequence is called, which can essentially establish some handshaking or initialization of some state machine that is required in managing the hardware. And as we remove that module out of the kernel, it will call the cleanup or the destructor sequence. We'll dive into this a little more, as we go along. Actually, a lot more as we go along. But for now, I just want you to remember: privileged, non-privileged, user space cannot talk to the hardware directly, must go through the kernel via a device driver. And the way user space talks to the kernel space is via the system calls, and the device drivers implement the system calls, and then there is this notion of constructor and destructor. So if you're clear with all of this so far, if you're convinced with this, in the next one, we'll dive into writing the kernel module.